All right, this is exam 3 for the online section of Physics 101, fall 2013. If a vault is opened by applying a force of 300 newtons perpendicular to the plane of the door, 0.8 meters from the hinges, find the torque due to this force about an axis through the hinges. So I have a door here, it rotates about here. I have a force that I'm applying here. So it's pretty simple. The torque is just the force times the moment arm times the sine of the angle. But my theta is 90 degrees, so the sine of 90 is equal to 1. So it's just the force, which is 300 newtons, times the length of the moment arm. That's this distance, which is 0.8 meters. 300 times 0.8, is that 240? Yeah. So A is the answer. Two identical bars are joined and shown, rotate about the dashed line, which has the largest moment of inertia. The moment of inertia is defined as mr squared. So we're going to look for the one with the most mass at the largest radii, and that will be A. It has the most mass, which is the mass of this entire stick, at the largest radius, and none of these others have that. And then it also has this bar, which has mass spread over all radii. This figure shows an arrangement of three particles. Oh, let's see. So the answer was A for number 2. Three particles rotating about a common axis. The axis bisects the 2 kilogram mass. The 4 kilogram mass is 3 meters from the axis. 5 kilograms is 2 meters from the axis. What is moment of inertia? Simple moment of inertia, discrete particles, sum mr squared. That is going to be the sum, 4 kilograms times 3 meters squared plus 5 kilograms times 2 meters squared. That's 4 times 9 is 36, plus 5 is 20. It'll be 56, which is A for number 3. Horizontal 100 kilogram merry-go-round, radius 1 meter, started from rest by a constant horizontal force. I'm going to find the kinetic energy after 3 seconds. All right, well, kinetic energy is 1/2 I omega squared. So we need two things. We need I and omega. Let's go and find I. This is a cylinder, 1/2 mr squared for a cylinder. That's 1/2 of 100. That's the mass. That's the radius, which is 1 meter squared, so that's 50. Now I want to find omega. Now to find omega, I have to go through a couple of steps. So just separate some of this. Omega is equal to omega naught plus alpha t. Right? But omega naught is 0. I know t, that's 3 seconds, but I don't know alpha. So I can find alpha because I know that my torque is equal to I times alpha. So alpha is equal to the torque over the moment of inertia. The torque here is 50 newtons applied at a radius of 1 meter. So it's 50 newton meters divided by I, which we found to be 50 as well. So my alpha is 1 radian per second squared. And now I can find omega, which is just going to be 1 radian per second squared times 3 seconds. So it's 3 radians per second is my omega. All right, so now I can go back to what I was originally doing. That's up here for kinetic energy. So it's going to be 1/2 of 50, which is my moment of inertia, times 3 squared. 25 times 9. 25 times 9 is, well, it's going to be 230. Yeah. Right? Let me just double check that. Yeah, 225 or 230. All right. What is the net torque acting on this bar about the point C? I want to know the net torque acting about this bar. I'll call this torque 1, this torque 2, this torque 3. Well, first one, ask myself which is positive and which is negative. Remember, clockwise torques are negative. This is clockwise, and this torque is 0, and this one is counterclockwise. I say this one's 0 because the angle between the moment arm and the force is 0 degrees, or 180 degrees, however you look at it, and the sine of 0 or the sine of 180, they're both equal to 0, so that torque is 0. All right, so now I just want to do my sum of my torques equals negative torque 1 plus torque 2. That's going to equal 12 newtons times this distance, which is 1 meter. That's a sine of 30. This is negative, plus 25 newtons. And this distance, which is also 1 meter, times the sine of 90, which is 1. And if I do that calculation, I get the answer. It's going to be positive 19. Since it's positive, it is counterclockwise, but we know that because 19, the only one with 19 is counterclockwise. All right, a merry-go-round has a mass of 100 kilograms and a radius of 1 meter, spinning at 2 revolutions per second. A kid jumps on. What is the angular velocity? All right, this is an angular momentum problem. That is that Li equals the final angular momentum. I have this disk, it's spinning around, and then I have a kid that jumps onto the outer edge and increases the moment of inertia, which is going to slow it down. So I already know it's going to slow down. That'll get rid of a couple of answers. That'll get rid of B and D. So now we're just left with A and C. We want to know by how much does it slow down. All right, so first we need, let me show here. So this is going to be I initial, omega initial, equals I final, omega final. We know omega initial. We need to find I initial, which is just for the disk. That's going to be 1/2 mr squared. That's for a cylinder. This is similar to what we had before, same thing. So it's 50 kilogram meter squared. It's the same as in problem number 5. And then when the kid jumps on, I final, it's going to equal that for the disk plus mr squared, where mr squared represents the moment of inertia of the kid, treating him as a discrete particle. So it's going to be 50 plus the mass of the kid was 50 times 1 meter squared. So I get 100 kilogram meters squared. All right, so my moment of inertia goes up by a factor of 2. That means that my angular velocity is going to go down by a factor of 2. So that's going to make it C is the right answer. Well, let's go ahead and work through this here. Just putting in the numbers here, I have 50 times omega initial, which was 2 revolutions per second, is equal to 100 times omega final. And solving for that, you get omega final equals 1 revolution per second. So number 6 is C. Which state of matter is associated with very highest of temperatures? That would be the plasma, or fully ionized gas. So it's so hot that the gases, the electrons and protons of the gas are separated, fully ionized. When you drink liquid through a straw, which of the ions listed below is primarily responsible for this to work? That would be atmospheric pressure. So if I have a straw and I'm pulling liquid out of it, that's supposed to be a mouth. I'm just providing a small pressure differential inside my mouth. I just try to provide a very small low pressure, and it's actually the pressure of the atmosphere that's pushing down on the water that causes it to go up into the straw, and ultimately into your mouth. So the answer there was A. Stonecutter's chisel has an edge area of 0.5 centimeters squared, which is equal to this in square meters. Give a force of 45 newtons. What is the pressure exerted on the stone? Well, pressure is force over area. It's 45 newtons over 5 times 10 to the minus 5. Which is going to be 900,000 newtons per square meter, or pascals. For D, 2 beakers are filled to the brim with water. A wooden block is placed in beaker B so it floats. That means some of the water is going to overflow the beaker. Both beakers are then weighed. Which shall read the larger weight? Okay, I know that the buoyant force here, which goes up, it has to equal the weight of the block because it's floating. Those two forces have to be equal for it to float. I also know that the buoyant force by Archimedes' principle is equal to the weight of the displaced fluid. That is Archimedes' principle. And since the buoyant force is equal to the weight of the block, and since the buoyant force is equal to the weight of the displaced fluid, the weight of the displaced fluid is equal to the weight of the block. Right? So even though you're adding the weight of the block, you're losing the displaced fluid, which has the same mass. So both are going to have the same weight for number 10. How deep under the surface of the lake would the pressure be double that at the surface? Right, so if I imagine the lake at the pressure at the surface is 1 atmosphere. All right, so I want to know where in the lake is the pressure equal to 2 atmospheres, or 2 times 10 to the 5th. So I want to know H for this. So say P is equal to P naught plus rho GH. My P is 2 times 10 to the 5th pascals. (1,000) H. And then I solve this for H. So that's going to be 1 times 10 to the 5th divided by 1,000 times 9.8. The answer then is going to be D, 10.2 meters, or about 30 feet. In fact, if you're a diver, you know that every 30 feet, I think it's 33 feet that you go out, that you increase your pressure by an atmosphere. And we see that here. Let's see, number 12, a blood platelet drifts along a flow of blood through an artery that is partially blocked. So I have this artery that's blocked, and this blood is flowing through it. I want to know what happens to the pressure. Well, by the equation of continuity, I know that the velocity has to increase, and when the velocity goes up, pressure goes down. That's Bernoulli's principle. So the pressure will decrease. In fact, you can get such a blockage that your pressure decreases so much that you just get a collapse of the artery altogether. All right, a heavily loaded boat is floating in a pond. The boat sinks because of a leak. What happens to the surface level of the pond? All right, the surface level of the pond is going to go down. Imagine this. I have this boat. It's displacing a lot of water. It's displacing so much water that the weight of the water is equal to the weight of the boat. Because boats are usually made out of things that sink like metal. However, when the boat sits on the bottom, it's not displacing nearly the same amount of water. So the level of the lake actually drops. Solid rock suspended in air by a spring scale has measured a mass of 9 kilograms. When the rock is submerged in water, the scale reads 3.3 kilograms. What is the density of the rock? All right, so this is my apparent mass, and this is my actual mass. I can find the buoyant force is going to equal the weight minus the apparent weight. All right, so that's going to be 9 times 9.8 minus 3.3 times 9.8. I'm just taking the difference in those two weights, the weight, the actual weight, and the apparent weight. And that gives me a buoyant force of 55.9 newtons. And now I want to know that the density of the rock, density is equal to the mass of the rock divided by the volume. I know the mass of the rock, it's 9 kilograms, so I want to know the volume. But since I know the buoyant force is equal to the density of the fluid times the volume of the object times g. So I can find then the volume of the object. That's going to be the buoyant force, 55.9 divided by 1,000 times 9.8. I get 0.0057 cubic meters. And now I can find the density. So it's going to be 9 kilograms over 0.0057. I get about 1577, which is going to be B for number 14. Bernoulli's equation is based on the conservation of energy. That's in contrast to the equation of continuity. Or similarly, equation of continuity is based on the conservation of matter. These other things are not relevant. This is the equation of continuity. Archimedes' law is sort of on its own. All right, ideal fluid of density of this flows at this rate through a level pipe. The pressure in the fluid is given there. The pipe connects to a second level pipe with a bigger radius, and I'm going to find the speed of flow in the pipe. So it looks like this. Small pipe goes into a bigger pipe. I have a certain velocity here that is given, I think, 6 meters per second. I want to know what is the velocity here. All right, there's a lot of information here, but really all you need is the areas. There's that radius, and I have this radius. All right, so I'm going to use the equation of continuity. A1 V1 equals A2 V2. And I'm looking for, this is V1, this is V2, I'm looking for V2. All right, A1 is going to be pi r squared, 0.5 centimeters squared, times V1, which is 6 meters per second, divided by pi times 1.5 meters, centimeters squared. I'm not converting my units here because all my units cancel out anyway, and the pi's cancel. It becomes a fairly simple calculation. So 0.5 squared times 6 divided by 1.5 squared. I get 0.67. Let's see here, 0.67. The Kelvin temperature scale is based in part on which of these? Okay, not the condensation temperature, not the freezing point, not the freezing point of hydrogen. It's the triple point of water. All right, 88 degrees Fahrenheit is how many degrees Celsius? Let's see, I always forget this, so let's just look it up. You look on your equation sheet, you can find the conversion for Celsius to Fahrenheit or Fahrenheit to Celsius. So like the Fahrenheit temperature is 9/5 TC plus 32. Right, and so let's see, I have 88. Let's solve for TC. That's my Celsius temperature, and it's equal to 31 degrees Celsius. Let's see. Which of the following properties can be used to measure temperature? Well, we can have the color of a glowing object, the volume of the length of a solid. It's all of these. So these, we listed a number of different thermometers, things that you can use for thermometers, and these were all listed in that. Steel wire, those dimensions and temperature and that linear expansion coefficient. I want to know its change in length. So I know that delta L is equal to L naught alpha delta T, and I want to know what delta L is. So this is really just plugging in the appropriate numbers. 150 meters times alpha, which is 11 times 10 to the minus 6, times the change in temperature was 45 minus 10, or 35 degrees Celsius. And I get 0.058 meters, which is 5.8 centimeters. Room temperature, the coefficient of linear expansion for Pyrex glass is less than that for normal gas glass. So normal glass you put in the oven and it cracks because it expands too quickly. But Pyrex, because it has a lower coefficient, it doesn't expand as quickly and it won't crack as readily. 2 moles of nitrogen gas are contained in an enclosed cylinder with a movable piston. If the molecular mass of nitrogen is 28, how many grams of nitrogen are present? All right, this is the number of grams per mole. So I have 28 grams per mole, and I have 2 moles. I multiply these, and I get 56 grams. So 22 is C. And then the last one, 23. This was an ideal gas law on the temperature. PV equals nRT. So PV over nR equals T. The pressure is 1.5 atmospheres. That's 1.5 times 10 to the 5th pascals. The volume is 0.1 cubic meters. N is 10 moles. And R was 8.3 0.314. Calculate that. We get 180. But that's in Kelvin. All right, so we have to convert that into centigrade, which will give us minus 93 degrees Celsius. That's the one.